solve linear inequalities by graphing. We want them to be in slope-intercept form first before we graph them, so y's got to be all by itself. Number one, real nice, y's all by itself. It's in slope-intercept form. What's y-intercept? 2. So we start at 2. And isn't the slope 1/3? Even though that's x over 3, isn't that like 1 over 3 right there? So we'll put 4 points on there. Rise 1, run 3. Rise 1, run 3. Rise 1, run 3. And you have to decide what kind of line you should connect them together with, solid line or dashed line. We'll use dashed because this is doesn't have an equal to bar, so dashed. And then I'll show you some more little secrets to make this not so messy. Dashed. Then we have to shade. And remember the trick, if y is all by itself, the symbol will tell you where to shade. Since that's a less than, where do we shade, above that line or below it? Below. And you can kind of look at your y-intercept to realize that's above the line right there. This is below the line. But we don't need to make a mess of things because we're going to have another equation on here we're going to shade. Watch this. Real nice and neat, just indicating to myself that I'm shading below this line. Here I just put a few little belows. I don't want to make a mess out of this situation. You can shade the whole thing, but it gets messy. And then on the back side, when we graph 3 of them at the same time, it gets really messy. So just kind of telling myself, hey, I'm shading below this line right here. Next guy, y all by itself. Isn't 1 the y-intercept of that dude? And the slope is -2. So like I said, this is a real simple day today. Solid or dashed line on this one when I connect them together. That's a dashed. And where would you shade on this puppy? I'm getting too far ahead of you, sorry. Would you shade above it or below it? I would shade below. Here's the y-intercept. Isn't this above the blue line that I have right here? I want below. But what we're looking for, my friends, is where the red shade and the blue shade would overlap each other. You've done this in Algebra 1. Wouldn't that be in this region right here? So grab that highlighter and highlight this region. Kind of give yourself a nice little boundary, and then take your highlighter, and let's make it fatter, and highlight all of this. This region represents all of the ordered pairs that are solutions to this system, meaning any point in here will satisfy both of those inequalities. Would the point 0, 0 satisfy either of those inequalities? It satisfies the red one, correct, but does it also satisfy the blue one? 0, 0, let me do a green dot. Here's 0, 0. Does it satisfy the system, yes or no? No, because it's not in the highlighted region right here. 0, 0 will satisfy the red guy, which was this first one, but not the second one, so it does not satisfy the system. Yes? Positive 1 is my y-intercept? Yes, it would be. Why did I have a -1 for a y-intercept? My bad. I did have that to start with, and then when I slid to the next slide, when I graphed it to try to be a super smarty pants, it didn't have. So my bad, video people. This is the dashed line that you have right here, and it's all shaded in there. So yes, 0, 0 does work. And that's proof, once again, that teachers are human and we make mistakes just like everybody else. My bad. Let's hope the rest of this doesn't have mistakes on it either. Next, top guy. Is it in slope-intercept form? So let's do this. This will help us with the backside. Let's put a number 1 next to this dude, and let's put a little 1 right here where we got some room to do some work, wherever you're at, where you got some room to do some work, and let's put that dude in slope-intercept form. We can go ahead and do the first move in our brain. Don't we need to subtract x over? So you'd be left with 3y. Does the symbol switch? No. And it'd be a -x plus 3. Correct? And then we divide every term by 3. The symbol does not switch because we are not dividing by a negative. And that'd be a -1/3 x plus 1. Is everyone okay with that? Then we'll graph that guy right away. Starts at 1 on the y-intercept, Mr. P. Goes down 1 to the right 3. Down 1 to the right 3. 1 to the right 3. Solid or dashed line. That's a dasher. And then give yourself a little indicator of where you'd shade, just a tiny little guy, to help you for the next situation. I would shade below that dude. So, a little indicator. Shading below. Then the second guy, we'll put a number 2 next to it. Do some work for number 2. Put it in slope-intercept form. So I'll subtract x over. Right? Then we'd have to divide both sides by that negative 2. And what happens when you divide an inequality by a negative number? That symbol switches. So this would be a positive 1/2 x minus 2. But that symbol had to switch because we divided by a negative. Rise 1, 2. And we'll use a solid line to connect those puppies together. Solid line to connect them together. This is supposed to be shaded below. Remember, that trick only works if y is all by itself, and we got y all by itself, so it's supposed to be shaded below. So below the blue line is down here. I also want to be on the side where the red was shaded, and I'll give you options. Option A, well, how about using a pen? Option A, B, C, or D. Where is my highlighted area going to be? It's in D because I need below this and in the red shade, which is right there. So there's D. Where's my highlighter? I like highlighting. If you're a Mrs. Colwell student, you can just use a darkened pencil. It's up to you. I'm sure she'll have a darkened pencil, but I'm a highlighter fan. Ooh. Next guy. Holy macaroni. Absolute value of y less than or equal to 1. Well, we have to realize and go back to chapter 1 or chapter 2. I can't even remember what. I think it's chapter 1. Are the bars like all by themselves on one side of the symbol? So what we'll do is we'll take what's in the bars and set up two situations. Y could be less than or equal to 1. Do you see how I got rid of the bars? And then this is a less than, so it's disunion greater than or. That would mean and, right, instead of or. Y would be switch the symbol, switch the sign. Absolute value means set up two situations, whatever the bars are by themselves. So we set up what we saw was what we get without the bars, then we switch the symbol, switch the sign. Cool? And now we'll graph both of these. First dude, horizontal, vertical, or oblique if it only has a y involved with it. That's horizontal, and that'd be like the line y equals 1, but it's just y less than 1, so I'll get my well, too many at one time, Mr. P. We'll graph this. Should it be a solid line or a dashed line? Solid. So I'll get my red line here. That's a horizontal line, y equals 1, solid. And before I even try to shade that, I'm going to graph the other one before I want to shade. The other one's y is greater than negative 1. So that's again a horizontal line, but it's through negative 1, and it's solid because we had an equal to bar. And now we can shade. Didn't the first one say less than? So that means we would be below that. And this one is a greater than, which means we'd be above that also. So that would be shaded in this dude right here, correct? We could try test point if we wanted to also to see if that works. If we try 0, 0, which is in that region, 0, 0 is right here. If you put 0 in for x and y, there are no x's. We want to see is 0 less than or equal to, if I could speak, if 0 is less than or equal to 1, which that's true, right? We also want to see if 0 is greater than or equal to negative 1, which that's true. So this was the right region. Cool. How about the other guy? We got to graph this guy also. What kind of line is that? It's a what line? Vertical line. So is it solid or dashed also? Dashed. So we'll graph that vertical dashed line through 2 on the x-axis. Because it only had an x in it, it's vertical. Remember, if it's got both x and y, it's oblique. Then where would you shade if that's x greater than 2? To the right of it. And we're also going to stay in that boundary between those horizontal lines, so we'll take our highlighter and we'll say this is our feasible region right in here. There are all the solutions to this system of inequalities. Cool. Next one, you and neighbors can get that one done on your own, one thing at a time. So you can pause the video, get that puppy done. It's pretty interesting for this guy right here. If you graph the first one, you'd start out at a y-intercept of 5. Slope is 1, so boom, boom, boom. That'd be a solid line that you'd graph also. And where would you shade on the first dude? Where would you shade if we get the right? Above it. All right, so that's a little bit up here. 2, 2, 2, 2, 2, 2, 2, 2. Then we graph our second guy, which is also in slope-intercept form. Starts at -4, slope of 1. Interesting. Those two lines have the same slope. What's that mean about those two lines? They're parallel. But where would you shade on this guy? Below. We're looking where blue shade and red shade intersect each other. Where did that happen? So how many solutions? No solutions. Now, just because we had parallel lines doesn't mean there'd be no solutions. If this was an equation situation, that is no solutions. But we could have had solutions to this, even though there were parallel lines, if we would have shaded the other way. If the red line would have made a shade below and the blue line would have made a shade above, wouldn't there be some intersection of the shadings in that situation? So just because there's parallel lines does not mean there's no solutions. That's because you have to do the shading for the inequality stuff. Does that bring back some sweet memories for you from Algebra 1? Let's go to the back side. They ask us to graph this system of inequalities, and up top in the instructions it says that when you do so, it's very possible for a polygon to show up. So let's graph it first, and then we'll kind of talk about the polygon that shows up and where the vertices are. First one is y all by itself. Yep. So we can graph that real easy. Y-intercept is 7. Slope of -3. Xander, solid line or dashed line? Solid. Why? Which part of that really matters? And it's a less than anyway, not a greater than. Because of the equal to bar. Where would we shade, my friends? Above or below? Below. So just real light indicator of here's where I'm shading. You don't want to make a mess. The more inequalities you have to graph, the messier it becomes. Second dude. Horizontal, vertical, or oblique. This y is less than 1/2 x. Horizontal, vertical, or oblique. It's still got x's and y's in it, right? What's the y-intercept? 0. Rise 1, run 2. Boom. Ooh, I like that. When I rise 1 and run 2, did I get a point on top of another point? That's going to be nice for us. But let's still put 4 points on top of there. This will be a dashed line, correct? A dashed line. And where would we shade on this bad boy? Less than means we shade below. Now watch this. I'm not going to make a super mess. I need to be below this line. I'm also wanting to be in the same region with the red, so isn't it only just in this zone that I care about so far? Who cares about over here? That does nothing with the red line, so it's like all out of bounds already. You with me on that? What we also should do is we should number these equations. It'll make things a lot easier. So wasn't our first equation number 1 right here? Let's put a 1 there and a 1 by one of the arrows in the line. And we'll call this equation number 2, and we'll put a 2 by it. That'll help us find the vertices later once we get that far. And let's graph number 3. Isn't that a horizontal line? So, and it'll be dashed. And put a 3 by it also. And where should that be shaded, above or below? Above. And do you see how that forces all of our shading? We had to be in this region red, in this region blue, and above it here in green isn't this little triangular spot right here where all our solutions are. So if you try to not highlight it a million times with a highlighter, but just once, that region is where all our solutions are, and it formed a polygon. We want the vertices of that. Why? For something that we're actually not going to do this year called linear programming, but these vertices really help in a real life situation, in situations where you want to like maximize your profit, minimize this, or what's your cost going to be to minimize cost. Finding these vertices is very important. So the vertices are where the lines intersect. First, let's do lines 1 and 2. Let's give ourselves a little indicator here. Lines 1 and 2. Where do lines 1 and 2 intersect? Can we see that nice and neat on the graph? Right here. What is that ordered pair? At 2, 1. Is everyone cool with that? So notice how above that I put lines 1 and 2. Right? Saying they intersect there. Now let's do lines 2 and 3. Do we have a nice, neat place where they intersect 2 and 3? Where's that at? Yeah, 2 and 3. So -4, -2. Someone said the answer to where 3 and 1 intersect. Just be careful which ones you're looking at. That's why putting those, excuse me, those numbers really makes a difference. And then lines 1 and 3. So we did lines 1 and 2, 2 and 3. The last ones will be 1 and 3. They intersect at 3, -2. And that was real easy because we could see where we got dots on top of other dots in the graph. That was beautiful, right? So when you're graphing these, sometimes maybe putting more than 4 points is a good idea, to where you can try to see where you get a dot on top of another dot. But sometimes that won't happen either, and we'll have to figure out where they intersect another way. Let's try it again, though. Let's call this dude number 1. Kind of line, x greater than -3, horizontal, vertical, or oblique? Vertical. Goes through -3 on the x-axis, and it is dashed. Shade. Where are we shading? To the right. Just a little helper shader. Second dude, put a little 1 by it in our picture. This is line 1. This helps us find our vertices a lot easier. And number 2. Y-intercept of 3. Slope of -1/3. Now do you see how I'm kind of, when I go down 1 to the right 3, I'm like moving away from the red line. Down 1 to the right 3, down 1 to the right 3. I'm trying to get a dot on top of another dot. So instead of going down 1 to the right 3, down 1 to the right 3, where else could I go to get closer to the red line? Up 1 to the left 3. Boom! There's a nice, neat place for me right there. We're looking to get those dots on top of dots. Dash line through them. But I still want as many dots as I can possibly, I shouldn't say as many as I could possibly get, but I want a bunch of dots because I'm going to have a third line in this situation also. See where that intersects. But where's this dude shaded, this blue dude? If we put a 2 by it, above or below? Below. So I don't care about any of that other stuff that has no intersections. Who cares about you out here? I care about all this stuff because it's in the red shade. Now I got some blue shade. Now let's finally get my green guy, which is still an oblique line. My intercept of -1. Got a slope of 1, and let's get dots on top of dots. Boom! Happened right there. And I'm going to keep working my way back down to the red line. Boom! Happened right there. I put a bunch of points on there to where I got dots on top of dots. Dash line. It'll be shaded above, which would put our highlighted final region in this zone. That's a tiny highlighter. Let's get a little fatter. In this zone. And hopefully to this point we're real comfortable, because these first 6 examples were supposed to be real peachy and nice and neat, and everything came out wonderful. The other 2 don't happen that way. But we need to do our vertices, so lines 1 and 2. If you keep doing things in the same order, I'll never give you, well, I shouldn't say that, but on all of these, there's 3 lines. Sometimes there'll be 4 lines in the picture, but keep in order, 1 and 2, then 2 and 3, then 1 and 3. The more consistent you are, the easier it is. So 1 and 2 intersected right here at -3, 4. Lines 2 and 3 is what I'll do next. 2 and 3 are right here. 3, 2, is that right? 3, 2. It's hard for me to read my graphs, it's all messy. And finally, lines 1 and 3 intersect at 1 and 3 from here. -3, -4. Let's erase that. Finding these vertices does have a real life practicality. We just, to save time, are not doing those problems this year. Maybe we'll do it at the end of the year. Who knows? Helps you maximize profit, minimize costs, stuff like that. Do we feel pretty decent as to this point? Next ones. Not so pretty on all of them. On 7, they're all in slope-intercept form, so let's get them all graphed and numbered. If you want to pause the video to get that done, you can do that. But graph, number, and shade, and then we'll find our vertices back together when we're ready for that. So pause the video, get that done for me. So by graphing, we look like this. Here's our feasible region. And it turned out that lines 1 and 2 intersected at a nice, neat place at 2, 2. And lines 1 and 3 intersected at a nice, neat place at -2, 4. But lines 2 and 3, we don't get a guess, right? We have to use algebra to solve it. We need to figure out where the green line and the blue line intersect each other. What I'd ask you is, how would you want to do that? You could graph the 2 lines on the graphing calculator, yes, and figure out where they intersect. That's one method. Let's think of all the methods that we've learned so far. So we could use the graphing calculator. Whatever line 2 is, punch it in. Whatever line 3 is. Here's my question about that, though. Do you always get nice, neat answers from the graphing calculator on the graph deal? Sometimes they're nasty decimals, right? So it's an option. Let's see what other options we have. What else could we do? That again. We could solve by substitution where 2 and 3 intersect. Couldn't we substitute this in for y? Change it to an equal sign. We don't need the inequalities. We want to know where this green dot and that blue line intersect. So isn't that like trying to just say where they're equal to each other? Right? We could solve by substitution. We could do that, which honestly wouldn't be very hard at all. Wouldn't we just do 1/2 x plus 1 equals 3x plus 10 and solve for x? Couldn't we do that? Now, before we do that, is there any other ways that we could do this? We could use elimination if we wanted to, right? We could solve a system by elimination, correct? Is there any other ways we could do that besides elimination, substitution, or graphing calculator with the graphs? There's one more way. The easiest way of them all that you just took a homework quiz about. Use a matrix. We could use a matrix to figure this out. Can't we do that? Aren't these linear? Right? So what would you want to do? Use the graphing calculator, use second calculate, intersect, solve by substitution, solve by elimination. What would you want to do? Let's do matrix. Cool. But here's the hardest part about the matrix is you got to figure out which 2 lines you want to see where they intersect at, and then you got to put them in x, y equals number order, right? You want them in that order. That's our comfortable deal. Don't we want lines 2 and 3, correct? So let's make ourselves an augmented matrix for it, but I need x, y equals number, correct? Here's line 2, right? Line 2, right here. Wouldn't the x have to come to the other side of the symbol? So what would that become? -1/2 first. Then the y is next. It's on the correct side. Isn't that a 1? Then our bar. And what's our constant equal? 1. We could do that. How about line 3? Isn't that the line that we're trying to see, lines 2 and lines 3, where they intersect? What would we have for our numbers here? -3, because the x has to come over here. 1, and then a 10. Correct? Now, let's use our calculator to figure out where they intersect. Which, honestly, doing it by substitution is just as easy, but graphing calculator time. Do-do-do. Do-do-do. I need a second matrix. Edit my 2 by 3. And you can put negative 0.5 in if you want to. You could put negative 1 divided by 2 in parentheses. It would work for you. But, oops, hit enter, delete, enter, 1, enter, 1, enter, negative 3, enter, 1, enter, 10, enter. What am I doing? How did I get out of there? You dirty dog. Sorry, video people. I had a boo-boo. Enter. 1, enter, 1, enter, negative 3, enter, 1, enter, and 10, enter. Now how do you go back and do that again? You quit out of it, and second matrix, what are we going to? Math, reduced row echelon form, which is choice B, correct? We've got to select whichever matrix we were. Mine was matrix A, so boom, and bang! Ooh, decimals. How do I change them to fractions? Math, enter, enter. Which always works, right? So now we can write this down, or honestly, can you tell me what the two answers are? What's the x value? Negative 18/5, and what's the y value? So you can. I want to see the augmented matrix for sure. You will get answers on this. You should know that ahead of time. You should not get a no solutions or an infinite solutions. How do you know you won't get no solutions or infinite solutions? You got a graph of it. Can't you see that they intersect in one place? You better find that one place. So it will come out real neat. What was it again before I pull up my calculator? Negative 18/5 and negative 4/5. If you want to put decimals below that, like if you didn't want to do math enter enter, to have it make more sense of negative 3.6 and negative 0.8, right? Which one makes more sense to you if you were to figure out where it was on the graph, the decimals or the fractions? It doesn't matter. I want them both, to be quite honest with you. You know, unless it was a nasty decimal, but those are nice, clean decimals. Could you find this, negative 3.6, negative 0.8, a lot easier than negative 18/5, negative 4/5, if I asked you to plot an ordered pair? It's whatever you want to do. I don't care, but I want them both if they're neat decimals. If it's a nasty decimal, give it to me as fractions. Okay? Next, let's roll with it. Top guy, number 1, it's not in slope-intercept form. So I'll put a 1 here. I'll do a little bit of work over here with a 1 by it and put it in slope-intercept form. Realize if you should switch the symbol or not switch the symbol. Then I'll graph it. Check yours with mine. Starts at 5, down 5 to the right 4, down 5 to the right 4, and that's dashed line, right? And shaded below it. Put a 1 by it. There's line 1. You want to try to put as many points as you can because you're hoping to get a dot on top of another dot. If it doesn't happen, I would probably solve that system with the matrix. Then, number 2 is already in slope-intercept form. Goody for us. See if we get a dot on top of a dot. Rise 2, run 1. Oh, that ain't happening at all, is it? Rise 2, run 1. I still want to put as many points, I shouldn't say all of them, but a bunch of them. Mrs. Colwell will probably have you put all of them, so do what she's been telling you to do. And then that's a dashed line again. But I can already see that they intersect in a nasty place again. Where's this one shaded? It's a less than, so that's a below. And then finally, line 3, I'm going to have to do some work for. All you really need to pay pay the closest attention to is should the symbol switch or not. Oh, crud almighty. That's not what I wanted to do. Did you get a y-intercept of -4/3? Yeah, so did I. I don't like that. But it's the way it is. How do you graph that? Well, what I would do is punch that equation into my graphing calculator and use the table of values to see if there's any nice, neat points on that puppy. So if I go to y equals and clear everything out that I had, you've got to punch that in correctly in parentheses. All your fractions need to be in parentheses. So 1/3 in parentheses, the x is on the outside. Then subtract away 4/3 in parentheses, like so, right? And I'm not wanting to see a graph of it at all. I just want the table of values to find some nice, neat points. So second table, maybe. And can we see any nice, neat points in this puppy? So let's make a little table right here, x, y. Just from what I see, I got a -2, -2, right? And I got a 1, -1. And that's enough. I will show you what to do after that. All you need is one. I will show you why. All you need is one nice, neat point. But you find some. All right, now let's go back to our graph and graph that puppy. I'm going to plot those points. -2, -2. Isn't that right here? Correct? All you need is that one point. Because after that, shouldn't you be able to use the slope from that one point? What is the slope? 1/3. Rise 1, run 3. Rise 1, run 3. Look at that. Isn't that at 1, -1, which was that other nice, neat point right there? So once you find a point on the line and you know the slope, you can just rise and run. So rise 1, run 3. Boom! That's a nice, neat place right there. Red dot and green dot. Rise 1, run 3. Maybe 1, 2, 3. And go down 1 and to the left 3 over here. And it looks like the blue line and the green line aren't going to intersect each other in a nice, neat place either. But I'll put a number 3 next to it. And then I'll grab my highlighter and shade the feasible region. I used my graphing calculator to find some nice, neat places. On this slide, I have a bunch of ordered pairs listed. But after doing a bunch of those, I realized, oh, duh, once you have one point on the line, you can use the slope of 1/3 to just rise 1 and run 3 from that point. Rise 1 and run 3. We're just used to getting that one point on the line being nice and neat, like the y-intercept all the time. Well, this y-intercept is still at -4/3. It's just nasty. So why not start on a neater place and rise 1 and run 3? Cool? So let's find our vertices finally. It's lines 1 and 2. Lines 2 and 3, and lines 1 and 3. Which combo gave us the nice, neat place? 1 and 3 intersected at 0, 4 or 4, 0. Where's that at? X first, Y second. Cool? The other two places were nasty, so I'm going to use matrices to help me find those. So watch this. Let's find where lines 1 and 2 intersect at first. I'm going to put a nice, neat augmented matrix right next to them. Line 1, is it in the right order of x, y, symbol, constant? So our augmented matrix would be 5, 4, bar, 20. Correct? And off to the side, watch what I'm going to do. I'm going to put a little 1 next to it outside my matrix. Say that was line 1. Right there was line 1 right there. Line 2, don't you have to subtract the 2x over? So that's -2, 1, 3. Is that good with you? Now use your matrix to figure out where they intersect at. So I'll get back to my calculator. Quit out of my table. Second matrix and edit it. I wanted 5, enter, 4, enter, 20, enter. Got it entered. I'll quit out of it. And I'm just going to use that second entry it says, do you want your answer as a fraction? That's not really what I want. How do I get up to that entry above it? Second entry again, and it's saying, did you want reduced row echelon form on matrix A? Yes, that's what I want on matrix A. Woo! You see how really nasty those decimals are. That's where we would not put our answer as a decimal. We would math enter it. And aha! That's very nice. So let me find where my vertice answer spot was supposed to be. Which lines were these again? Oh man, I forget. Which lines were these? 1 and 2. So my x value was 8/13, and my y value was 55/13. I'm not going to make you write that reduced row echelon form matrix down on these simple ones because we know we're getting an answer. It's good enough. Now do that for 2 and 3. Lines 2 and 3. You need to write a new matrix though. So lines 2 and 3, I'll come on here and do my new matrix. Hey, my number 2 will still be the same. Won't it be -2, 1, and 3? Isn't that still my same numbers for my number 2 matrix? Number 3 would be 1, -3, and 4. I got a question for you. If I switched them around, if this was matrix 2 or line 2 and this was 3, what if I put 3 on top of 2? Would it still give me the same answer? Yeah. It's just, all this is, what we're doing is a fancy way of solving a system by elimination. That's what reduced row echelon form is. But just retype it in. So 1, 3, enter. 1, enter. -3, enter. 4, enter. Quit out of it. Second entry a couple times to get back to what I wanted, and hit enter. Nice neat decimals. You can put those, but I also want them as a fraction also. So I'm going to say at -2.6, -2.2, and then as the fraction, I'll math enter that, and it'll tell me it was at -13/5, -11/5. Once you learn how to use this calculator, it'll be the greatest thing you've ever bought in your whole life, math-wise. Cool? So, on the homework from here on out, when it says solve the systems however you want to, if they were linear systems, what would you personally choose for linear systems? Matrix. Now what about the ones with the squares and all that stuff? Are those linear matrices? So you have to use a by hand method.